Let's start off by discussing polar coordinates. As you know, in two-dimensional space, if you want to describe the location of a point, you can use the polar coordinate scheme. That is, after you select the axis and origin, you can use the distance from the origin to your point, which is this r. You can use this r and this angle theta that this line makes with the x-axis. You can use these two pieces of information to talk about the location of any point uniquely. Alright, so that means that you can actually use polar coordinates to describe any kind of two-dimensional motion. But it turns out that they're especially helpful if you have circular motion. What's circular motion? You have a particle that's rotating about a point in such a way that its distance from that point is always constant. So naturally, what you'll do in circular motion is the following. You'll take as your origin the point about which your object is rotating. Then this r is always going to remain a constant. It's some constant value, right? And with time, theta is going to change. Notice how we are selecting theta. We are selecting theta in such a way that anti-clockwise rotations correspond to a positive change in theta, right? So that if this particle is moving anti-clockwise, then theta keeps increasing. So an anti-clockwise rotation makes theta increase. Okay. To make full use of our polar coordinates, we need to set up unit vectors r hat and theta hat. It turns out that this is much more subtle than the simple I hat and j hat we had been using in Cartesian coordinates. So let's suppose we have a particle moving in circular motion about like some origin O. Suppose at some time we've got the particle here at point P. How would you set up the unit vectors at point P, right? So we would have at P r hat as a vector that points radially outwards. What does that look like? So at point P, r hat, a unit vector that points radially outwards, would look like this, right? So what's theta hat? We would take theta hat to be a unit vector that points, first of all, perpendicularly to r hat, and it will point in the direction of increasing theta. In which direction does theta increase? Well, basically theta increases in the, theta is this angle, and theta increases in the anti-clockwise direction. So a vector that's number one perpendicular to r hat, and number two points in this increasing direction of theta would of course point in this direction. Okay, but now notice an interesting subtlety. We've done this at some point P. What if it were at some other point Q? Okay, at P, instead of calling them r hat and theta hat, let's subscript them. Let's call it r1 and theta hat 1. Think about some other point along the motion of this, along the circular motion. Like, let's say, think about this point here. Let's call it Q. Then at point Q, if you try to apply the same prescription again, you would have an r hat that points in this direction. Let's call this r hat prime 2. And theta hat would again point in the direction of increasing theta. Theta increases anti-clockwise, and then you would have the theta 2 going like this. That's interesting. What does that tell you? That gives you a very important point. The important point being that in polar coordinates, we have different unit vectors at each point in space. So what that means, what that looks like is that r hat 1 is not equal to r hat 2, and theta hat 1 is similarly not equal to theta hat 2. This is very different from the Cartesian scheme that we've been using, where really in the Cartesian system, so we've had an I hat in this direction and a j hat in this direction, and we would have the same I hat and j hat at each point in space. But that is no longer true if you choose these polar coordinates. It might seem like an added complication at first, but we shall see how helpful this is when describing circular motion. But first let's take a moment to convert between our new polar unit vectors at some point to the familiar Cartesian unit vectors. So how do we do that? Let's say we have our particle here at some point P, which is at some fixed distance from the origin, right? Which is the radius of the circular motion, but we have it at some angle theta. So of course r hat and theta hat are we are trying to take unit vectors here. So r hat has a magnitude of 1 and theta hat also has a magnitude of 1. Now because I hat and j hat simply point along the x and y axis at each point in space, we can easily resolve this r hat into its components. So r hat would be mod r hat cos theta I hat, right? Because cos theta is this length here, and you would have plus mod r hat sin theta j hat, because sin theta is this length. And because mod r equal to 1, we finally get this r hat equal to cos theta I hat plus sin theta j hat. And by a very similar argument, you can show that theta hat equal to minus sin theta I hat plus cos theta j hat. You might find this formula very useful later on. Let's use our unit vectors to talk about the position vector of a particle moving in circular motion at some time t. So here we have a particle that's moving with respect to this origin in circular motion. Suppose the particle is in the place shown at some time t. Then the radius, so the length of this green arrow is r. The position vector is given by that arrow rt. Now what's the unit vectors at the position of the particle at time t? So the particle is here at time t. We would have a unit vector that looks like this. R hat would be 1. Of course, this is a function of time. What we mean is that at some other time, your particle would be at some other place, and then the r hat vector would look very different, right? So the unit vector at the position of the particle at time t changes with this time, right? So anyway, you would also have another theta t vector that looks like this. And as we knew how these r hat and theta hat were given in terms of the Cartesian unit vectors I hat and j hat. We'll just need to understand that this angle, which is theta, changes with time because this particle is moving. So this is a function of time, theta t. Just plug that into the expression we had a minute ago, and you'd have r hat t equal to cos theta. Now theta is a function of t, so cos theta t I hat plus sin theta t j hat. And a similar expression for theta hat. Now that we have the unit vector, now that we have the polar unit vectors at the position of the particle at time t, it's very easy to talk about the position vector at time t. We have, in polar coordinates, we would have RT. So what's RT? RT is this arrow right here. RT has a magnitude of r, and at time t it points in the direction of r hat t. So very simply, and this shows us why polar coordinates are so good in talking about circular motion. The position vector is simply given by r times r hat t. What would it look like in Cartesian coordinates? Well, you could just plug this in, right? And we can say that in Cartesian coordinates, the position vector would look like r t equal to r cos theta, but theta changes with time, so cos theta t I hat plus r sin theta t j hat. Of course, now that we have the position vectors at time t, how would we find the velocity at time t? Just differentiate, right? Okay. So the velocity vector at time t, vt, is given by vt equal to dr t by dt, which is now given by d by dt r times r hat t. Of course, in circular motion you would have r equal to some constant, and you pull that out of the differentiation, you have r d by dt r hat t. This unit vector r hat t is different at different points on the motion, right? So it makes sense that this can be differentiated with respect to time. Let's look at how that looks. So you would have this equal to, let's jump into this Cartesian coordinates for a minute because the differentiation is easier to do there. So you would have d by dt cos theta t I hat plus sine theta t j hat. How do you do this differentiation? It turns out that this differentiation is given to you by r. So of course I hat and j hat don't change with time, so that in doing this differentiation it's a little simpler. You would have minus sine theta t d theta by dt I hat plus cos theta t d theta by dt j hat. Do you know what we did here? We did use something here called the chain rule. So let's look at what that is. We used chain rule where, let's look at an example of what that's like. For example, if you want to differentiate, let's say d by dt cos 2t, how do you do that? First you differentiate the function cos theta, so you write minus sine theta, theta equal to 2t, right? But then you multiply that with d of 2t by dt, right? The argument of the cos function here. You have to differentiate that and multiply. So we did basically the same thing here, right? With cos theta t, we differentiated that into minus sine theta t, and then we differentiated the argument d theta by dt. This is called the chain rule. Okay, so now we can take d theta by dt common, and what we have, very interestingly, what we have now is r d theta by dt theta hat t. Interesting, right? Because we had, of course, theta hat t was, theta hat t was minus sine theta t I hat plus cos theta t j hat. Isn't that very interesting? Both the position vector, which was r times r hat t, and the velocity vector, which turns out to have this form r d theta by dt theta hat t, have a very cute look in polar coordinates, right? Well, now that we've shown that vt equal to r d theta by dt theta hat, or v theta theta hat, where v theta is a constant, we can talk about all this in a bit more detail. So some important points to note are, number one, as we know, if we have some kind of motion, the velocity at each point of the trajectory is tangential to that point, right? So what are theta hat? For example, if we have a circular motion here, and at this point we've shown the theta hat is a vector that looks like this, right? You would expect the velocity vector at this point to be parallel to this theta hat, right? So this result that we got, where vt equal to v theta theta hat, this is what we should expect for velocity. Now, because v theta is a constant, it could take on values greater than 0, or v theta equal to 0, or v theta less than 0. Let's look at those cases one by one. Because v theta equal to r d theta by dt, where r is a positive constant, what does that tell you? If v theta is greater than 0, that means that d theta by dt must be greater than 0. And what's d theta by dt greater than 0? It means that this theta angle is increasing. How would theta angle increase? If the particle moves like this, right? So this would correspond to an anticlockwise rotation. By the way, what does the velocity vector look like if v theta is greater than 0? So suppose at this point the velocity vector should point in the same direction as theta hat if v theta is greater than 0. After all, v equal to v theta times theta hat, so it points in the same direction as theta hat if v theta is greater than 0. Okay, what about the case where v theta equal to 0? For that, d theta by dt will have to be 0. In other words, this angle theta cannot change. This angle theta will have to remain stationary, and that just corresponds to the particle not moving at all. After all, r is a constant, theta is a constant, the particle stays where it is. And in the third case, where v theta is less than 0, that just tells me that d theta by dt is less than 0. D theta by dt less than 0 means that this angle theta is decreasing. That must mean that the particle is moving in a clockwise direction.